Hi and welcome to the Windows Process Injection Fundamental course here on Pentester Academy. My name is Pavel and I'll be your guide throughout this course. The last technique we're going to examine in this course is called process hollowing. The idea of process hollowing is to create a legitimate process such as a notepad or something else and then replace the executable code inside that process with some malicious payload. And so the process has to be created in suspended state. So the process exists, the main thread exists, but it didn't start executing any code from the original executable yet. And so what we need to do here after calling create process is provide our own malicious executable and map it in some way into the target process. Once we do that, we need to do some fix-ups, such as point to the new image from the process environment block, which is a user mode structure that is important to keep in sync with what's going on inside the process. And then once we resume the thread will start actually execution of our replacement image and not the original image that was there. And so finally we resume the thread and we're done. We don't need the attacker process anymore because we have a process that looks like, say, Notepad or Explorer or something else, but inside it something very different is happening. So this is the basic idea. So let's see how is that done. But before we look at that, we need to take a brief examination of the portable executable format or the PE format. And so the PE format is the basic format of all executable images on Windows. That means executables, DLLs, sys files, which are typically drivers, OCX, which are usually also like DLLs, like ActiveX controls, and EFI images for the extensible firmware interface images. They are all PE files, and they have this specific well-known format that is fully documented in the Microsoft documentation. As you can see here, you can go to that link and look at the entire documentation. And these are the files that are being loaded by the loader and then, of course, recognized and parsed appropriately and mapped into system space as they should be. Now, what does a PE file contain? So from a data perspective, it has three types of information. It could hold code, it could hold data, it could hold resources such as strings, icons, bitmaps, dialog boxes, and so on. And so as you can see here, there's part of this structure contains various types of headers with basic information like what kind of PE version is it for 32-bit or 64-bit, what kind of machine type it's appropriate for. So there's lots of information here in this file header and optional header, and then there's the actual sections. These sections contain the information itself. Some of the sections contain code, some of them contain data, some of them contain data which is used by the loader, such as a list of all the exports and the list of all the imports, whatever the image needs to bind to in order to work properly, and so on. And so for process hollowing, we do need to know something about the way the PE file structure is built, because we need to play the role of the loader when we copy our own replacement executable into the target process. We need to make it just like the loader has loaded it, as if. And so we need to know something about PE, and we'll see that in the code demonstration. So let's pop up to Visual Studio and see what that looks like. And so here's my main function. And what I want to do here is allow myself to provide an image name to create. That's going to be the hollowed process. And then a replacement executable so we can replace that code with this new code. Now, by the way, here I'm going to use an actual executable that is on disk, but in fact we can get that code from, let's say, command and control server. And so one of the advantages of using process hollowing is that we don't really have to have a physical file, which means we can just get the data from memory and just copy that to the target process, which makes this less detectable. But for this demonstration, I'm going to use an actual file, but that data can come from anywhere. And so we have these process we want to create based on that executable name called name, and then we're going to replace it with something called replace here. So the first order of business is to create that new process. I mean, this is what we want to do. We want to create a legitimate sort of process, but not let it execute. So I'm calling the create process A function here, providing the name here, which is the ASCII value of the executable we want to run. And I'm not going to go over the create process function in detail, but there are very few really important parameters. And so this is the name, which should be the path or a short name to the executable, which is also looked up in the standard lookup paths such as System32 and so on. So we can create something like Notepad or Explorer without any problems. And then we have this startup info object here, which provides extra information for creation. For our purposes, we don't need anything, so we can just go ahead and use this kind of initialization that sets the first field to the size of the structure and zeroes out the rest of the fields. And this is required because this sizing allows the Windows APIs to look at the correct size and not look beyond that, because this size is used as sort of a versioning in many structures in Windows. And so if the size is larger, then the API would look further, because that means the caller knows about a larger extended structure. And so we have to pass this structure right here, and the result of create process, if it succeeds, besides the true value that should return, is here in the PI parameter here, which is of type process information, which is populated by create process with the handle to the new process, the handle to the new thread, and the process ID and the thread ID that were created as part of the creation of the process. So I'm putting that in a global variable here for convenience, because if something fails during my attempt to hollow the process, I want to terminate that new process because I don't want to execute that normally. And so this is something I require here with process information, so I'm just setting that up as a global variable for convenience. And so the most important thing here with create process is using this flags parameter, and this particular flag create process is essential. This means I want to create the process, create the initial thread, do some initialization that is done by the loader, by NTDLL, and that is it. I don't want the executable to start running code just yet. And that is critical for process hollowing, because we want to run an alternative code. And so I'm going to just use create suspended. If it succeeds, we can go ahead and look at the next step. So here I'm just doing something for convenience. I'm setting the current directory to the directory where the executable where I'm running my attack application from, just so I can provide the replacement executable as a relative path if I wanted to, if it's in the same directory, but it doesn't really matter for our purposes. And then I'm going to have to open the file, which is the executable file I would like to replace the existing file. And again, this data could have come from anywhere, but in this case it's going to be a file, so I'm opening the file with the create file A function, providing that replace executable path that I got in the command line, and seeing whether that succeeds. I'm opening that for read access, and I'm perfectly fine for that to be written just as well, and I'll explain in a moment why that may be important. So I'm opening the file, making sure that it exists and everything is fine, and then I'm going to allocate in the new process, in the suspended process, a piece of data that is equal to the file size of the replacement executable plus some extra. In this case, I'm using 64 kilobytes of extra memory, and that's because when an executable is mapped into a target process in whatever process, it doesn't consume the same amount of memory. In fact, the sections are a bit kind of compressed, and then they need to be mapped to different pages in the target process, so it just is a bit larger in the target process when the image is actually mapped. So I'm going to just use some heuristics and add 64 kilobytes to the size of the allocation. And notice I have to allocate that with page execute read write, and that's because I'm going to map some code into that from the executable, and so it has to be executable. Of course, I can do that later with better granularity and put some of the sections as read-only, such as headers, but the code itself must be execute, so I'm going to just be lazy and put everything under execute, although in a real case you want to be a little more careful about that because this is a red flag for various anti-malware solutions. So we get this new address inside the target process. So now I need to copy my executable to the address I just allocated. Unfortunately, I can't just simply make the copy and be done with it. It's not that simple, and that's because I need to do the same thing that the loader does. And the loader needs to look for the imports, everything that the executable is using, and then bind them to where they are in real life. And because executables by default today are loaded into sort of pseudo-random addresses because of that ASLR feature I mentioned briefly in the previous demo, we can't just copy that easily. If we do make that copy kind of in a straightforward way, then we have to have a second step where we provide and do the fix-ups that the loader would do to make sure the functions are aligned to the new address in which that executable was mapped to. And so this is definitely possible, and if you look at various resources on the web, you'll see that many process hollowing examples do just that. But I decided to go in a different route, and what I'm going to do is call the rebase image 64 function. This is part of the image help API. I'm also, it's mandatory to add this lib file to link again so I don't get an unresolved external. And what rebase image 64 does, it actually rebases the image to a given address. And so I'm giving it the new image base as the new address I allocated in the target process. And so the image will be already ready to be run as is without any need to do any fix-ups. And so this is something that works because I have a file, and rebase image needs a file to work with. So if the data was coming to me as just memory from somewhere, I would have to do the rebasing myself. But in this case, I will let rebase image 64 do the hard work for me. And then what I need to do is map the executable, my replacement executable, to my address space so I can copy it to the other address space. So I can do that by just calling the read file function and then simply allocating a large enough buffer and do all that, but there's in fact a more efficient way, which is using something called memory mapped file, which allows me to map a file into memory. And so this is done by using the create file mapping function to create the file mapping object. This is called a section object internally in Windows. And then I can use the map view of file ex to actually map that file into the same address that it's mapped to the target process. So now I have these two pointers. One of them in my process points to the file, and the other one is the pointer to the other process, which currently has nothing, just allocated memory. So what I need to do now is do some PE parsing. It is not fun, but it's not too difficult. Once we understand the layout of the PE file, we have these various structures that are already defined by the Windows headers, and so we just need to read them and then copy the headers and then the various sections to the target process. So here's the address I have mapped my executable to in my process, and so I need to cast that to image DOS header. This is the first structure we've seen in the slides, and then inside that address there's an offset that specifies where the real header comes in, because this is kind of the old header that was used in DOS programs. And so once we get this pointer with the image NT headers structure, then we can get to the actual sections by moving to the end of the header. So NT+1 moves to the end of the header. This is where the section headers are. And each section header provides information about where that header is in the file and its size. And so here goes copying the information from the file to the target process, but copying the relevant information. So first we're copying the headers. So here we have the image base that we need to use from something called optional header. This is where we need to copy the headers themselves. Again, this is part of the PE format, and so you just have to read the documentation to understand that this is where we want to copy that to, and we're copying that to the new address, of course, from the executable that we have, and this is the size of the headers that we need to make the copy. And then we are copying the sections themselves, and so the file header is something called number of sections. This is number of sections we have in a file. And then we can use write process memory again in a loop, and this time copy that to the new address in the target process and offset that by the virtual address. And this is not really a virtual address, it's actually an offset. It's called the relative virtual address, or RVA in PE parlance. We need to copy to that offset beyond the base address. And here we are getting the pointer to the raw data. And again, we offset that with the image base, of course. And then this is the size that we need to actually copy. Now we can view that information a little bit differently, perhaps using a tool. So it's advisable to take a tool that knows how to look at PE files. And so I have one of those tools that I've actually built, but you can use any of the freely available tools to look at PE graphically, or use even the dump bin tool from the Visual Studio tools to view some information using command line. And so I can go ahead and open, let's say, any executable that we want. So here's Notepad, but let's go ahead and try to get to our own executable that we would like to inject. So that's going to be an executable called simple. So I'm going to go ahead and find this simple.exe and open that. And you can see that it has a bunch of sections. There are 11 sections here. We can go ahead and look at those. Here are the various types of sections. So for example, the .text section is the most of the code is there. And there's data sections and some other sections such as resources and so on. And so these are the sections we need to actually copy. I can go ahead even and look at this section as pure binary that is in there, and this is the data we need to copy to the target process. And so once we do this copying, the last step is actually fixing the image base address inside the process environment block. So a process environment block is a very important structure in user space that exists on a per process basis. And to get the pointer where that PEB is, we have to call the native NT-query information process function, unfortunately, with the process basic information value, enumeration value. And what we get back is something called process basic information. And in there is a field called PEB base address, which is the address of the process environment block. And in this case, of course, we're interested in the target process PEB. So we get the address here. And if you look at the real PEB, which is strictly not really documented, but of course reverse engineered and is available in the public symbols that Microsoft provides, we can see that image base address is here. After we have two machine words here, this 4 bytes is actually aligned to 8 bytes on 64-bit, and the handle is 8 bytes as well on 64-bit. And so this should be kind of two 64-bit values later, and so we're writing in the PEB by jumping two pointer-sized values to this member. And so if we're on 32-bit process, that's going to be 8 bytes. If we're using a 64-bit process, that's going to be 16 bytes. And we're writing the new image base that is available from the header. And we're almost done, because currently the thread is going to still try to execute the original process. And by the way, it is possible to really unmap the original executable, but in this case, I prefer to keep it inside. It will just not execute any code because this would make it more difficult to identify the process as hollowed, because the original image will still be there. It will still be mapped normally, it will just never execute any code. And so we need to tell the runtime or the loader, once we resume the thread, where to go next. And so what we're going to do is read the thread's context and then put the entry point of the executable that we've mapped to the RCX register for 64-bit and EBX for 32-bit. Why? Because this is what the NTDLL expects after resume thread is called in this scenario. This is something we just need to know. And so we take the new address in the target process and we add the offset that is coming from the header, saying, well, in that executable, where exactly is the startup code? Where is that CRT main or something that starts execution? So this is exactly this parameter. So we're pointing that to RCX, and then we can go ahead and provide the thread with the new value by calling setThreadContext. And then all we really have to do is just call resume thread and we're done. All this unmapping and closing of handles is just me being polite, but really it's not necessary because the process is going to shut down anyway, leaving the target hollowed process only running normally, but running our own code. So this is the basic idea. And we can try that with this simple executable. The simple executable, the only thing it does is just shows a message box like we've done previously and writing something like in hollowed process. So now we want to test that. So let's go to the command line. So now we want to test that. Let's go to the command line. And what I want to do here is run the hollow executable and select the process I want to hollow. Now I can use Notepad or something like that, but really what I want to use is something which is more stealthy, such as SVC host. Because SVC host, there are so many of those running around on a Windows system, and so another one coming up will not raise any suspicion. And I want to replace that with simple.exe inside that SVC host. And if we try that, we can see that we found and hollowed a process here. And in fact, we can go ahead and look at this address in the memory of that SVC host and see that in fact it holds some executable data. I'm not going to be able to look at the actual data, at least not with the tool that we're going to use right now. And so what I will use is a tool from sysinternals called VMMap. And so VMMap is a tool that allows you to look at some processes address space. So I need to find the SVC host. The problem is I'm not sure what the process ID of that SVC host is because there are so many of those. Let me just go ahead and try this again, but let's make a quick change to the application. Let me just add, after the create process success, say created PID and just display the process ID that we got inside the, this particular process information structure. So if I go ahead and run it now, I can see in the command window, oh, sorry, I need to run that from the command window. Let's do that again. And so the process ID is 32576. So now let me go to VMMap again and search for a process that is 32716. So let's see where it is. So this is it. Here's the SVC host we created. And now we can see the address map of that particular process. Now I'm not going to discuss this tool right now. Maybe we'll do that in a future video. But for now, we can go ahead and look at the private data. Private data is really all those virtual alloc calls. And we can see there's a chunk here, which is read, write, and executable. This is where we wrote our malicious custom executable that replaces the normal executable. And so this is the address. We can verify by going back here and looking at what we see here, we can see the address is indeed 24B52. This is exactly the address we see here. This is where we injected our custom executable, and it's running from there. So let's go back to the slides. And so what about the APIs we were using? We started with create process to create a legitimate process. Then we opened the file to our replacement executable. We allocated memory in the target process. We used rebase image 64 to make sure that the executable is aligned with the address it's going to be loaded into, so no fix-ups of imports are necessary. And then we did some file mapping so it's easier to copy from the source process to the target process, and used write process memory normally to copy the headers and the various sections. And finally, we need to do some fix-ups to the process environment block, so we used anti-query information process to get that pointer, make the change in the thread's context, and let it go by calling resume thread because it was created in a suspended state. So it's very difficult to conclude from a defender's perspective whether that process is malicious or not, because it looks normal and the executable code is still there, at least in the way I implemented that. And of course, the replacement code can be just in memory, which again makes it very difficult to locate and to identify because there's nothing on disk. So in our case, I did use a disk file, but in other cases, I could have just got that image from some network server. The cons is that it requires a new process, and so anti-malware solutions always monitor for new processes. However, because that's going to be a valid process, a legitimate process, such as Notepad or SVC host, the anti-malware solution would have trouble identifying that as malicious. And so detection is very difficult. If there's a file on disk, then opening the file will definitely trigger an event that the anti-malware solution can look at. But if it's not on disk, then there's really nothing to detect. And so that's a very stealthy way of providing some malicious code on a system. And this brings us to the summary of this module, and in fact the summary of this course. And so we looked at this module for various ways to inject code into processes. We've seen 5 ways of doing that, and this should give you an idea what can be done, and so you can go ahead and look at other more advanced techniques that you can find on the web, and perhaps have your own ideas of how to create custom ways to inject code into processes. And with that, I thank you for watching. See you in another course.